Hello everyone. In the last class, we discussed about preliminary seismic evaluation of reinforced concrete building. Today, we will take our discussion forward and learn about the detailed evaluation of reinforced concrete building from seismic perspective. At the end of the last class, we have given recommendations related to detailed evaluation. Once we are confirmed that we need to conduct detailed evaluation, then we have to follow some procedure. So, the first step in the detailed evaluation shall be to assess the condition of the building components and materials. This will include some non-destructive testing of the building as well. This is based on clause 7.1 of IS 15988/2013. I hope you have the copy of the code ready with you. Upon assessing the condition of the building components and material, we shall go for evaluating or assessing capacity and demand. We will find out the probable strength of different components of the primary lateral load resisting system. Here, in order to find the probable strength, we shall use the knowledge factor. If you recall from the last class, knowledge factor takes care of the information that we are having about the building, about its construction, about its maintenance, etc. Then we shall calculate the expected seismic demand, that is the modified lateral force and resulting member actions. This shall be based on various methods, whether it can be equivalent static method or the dynamic analysis method, and here we shall use the usable life factor, which takes into consideration that the existing building has to have a service life which is much lesser than a new building. Then based on this, we can compare the probable component strength against expected seismic demand on that very component to assess whether the building needs retrofitting or not. We shall also check various criteria which are called as acceptable criteria, and we will also do some evaluation related to ductility and detailing of the building. So, in today's class, we will look into these one by one as we move. So, the first thing, let us look into the condition assessment of building components and materials. So, the first thing is so when it comes to condition assessment of building components, then we shall look for various distress signs in the building. It can be in form of deterioration of concrete or cracks in various structural members or infill masonry walls. So, based on these deterioration signs, we shall be able to tell, or we shall be able to predict what is the reason or what may be the reason behind this distress. That will give a hint that what is the deficiency in the component of the building, which will help us identify or decide suitable retrofit strategy for the building. Now, let us look into some examples of common distress and try to establish the cause related to that. Let us say that if we have vertical cracks on beam soffit near midspan. So, these cracks are flexible cracks. How will flexible cracks develop? This implies that the longitudinal steel may be insufficient. That may have led to large tension forces at the soffit of the beam, typically simply supported beam, and in that case there would be vertical cracks on the beam soffit near midspan of a simply supported beam. If you observe inclined cracks on the beam sides near the supports, then in that case we can tell such cracks are shear cracks, and it might be due to the insufficient confinement in the beam. How do you get the insufficient confinement? If you have lack of transverse reinforcement, which means if you have large tie spacing or improper hook configuration, then in such cases you will have insufficient confinement in the member, which will lead to shear crack. Such cracks are quite common in deep beams. Then if you have diagonal cracks in column, this implies that the cross section is inadequate for the loading, or the loading may be excessive. The longitudinal reinforcement in the column may be inadequate. Further, if there is any differential settlement of foundation, then that can also lead to diagonal crack. So, there can be multiple regions which can lead to a distress sign. So, from one distress sign you can think of multiple 2-3 regions why it would have taken place, but based on different signs of distress in the building you can conclude what can be the most probable region. Then if you have buckling or longitudinal cracks in column, then in that case we can conclude that the transverse reinforcement would be insufficient, or your longitudinal steel would have corroded. Sometimes these can be a combined effort of all these regions. For example, if your transverse reinforcement is insufficient, then it will provide less confinement, it will lead to buckling or longitudinal cracks in the column. If there is some crack, then the ingress of water or moisture will be very easy, which will lead to the corrosion of longitudinal steel. The corrosion of longitudinal steel will lead to rust, which will occupy larger volume compared to steel. Larger volume will put further stress on the concrete which is not confined properly, and it will lead to widening of these longitudinal cracks. So, these are the common distress and cause establishment in a given building. You can have other forms of distress as well. For example, spalling of concrete from the slab. Think about this, why it can take place. Sometimes you may need to think about these causes from a mechanics perspective. Okay, so once we have the information about the distress signs, we can establish some cause or the most probable cause related to that. Now, let us also look into the condition assessment of building materials. Many a times you will find that the materials also degrade with time. How do you assess the deterioration of these materials, or what is the current condition of the material? Suppose if you have built a column with concrete which has 50 megapascal of characteristic compressive strength, that is M50 grade. Can you be sure that after 40 years the strength of the concrete in the column will be the same? It is not possible. It will deteriorate based on the environmental exposure. So, how do you estimate that? That you do using a lot of non-destructive testing and some laboratory testing as well. I have listed many non-destructive testing methodology over here, and for each non-destructive test or NDT, I have also shared the references, mostly Indian standards, for these tests, so that you can spend some time looking into these codes. What is the process of performing these tests? What is the conclusion, or what is the significance of these tests? Let us quickly summarize them one by one. Ultrasonic pulse velocity. This is a measure of quality of concrete, particularly from the context of density, homogeneity and uniformity. A higher UPV value, that is a higher velocity value, means better quality of concrete, lesser number of voids in the concrete. It is contained in IS 516 Part 5 Section 1 2018. When it comes to rebound hammer test, it gives you an idea of surface hardness and the uniformity of concrete. It does not give you a compressive strength of concrete, but there are calibration charts which are provided by the rebound hammer manufacturers, which can be used to estimate the compressive strength of concrete based on the rebound number what you get. But the rebound number is a direct indicator of surface hardness of concrete. It is not an indicator of compressive strength. We are only estimating the compressive strength. So, it is important that you use the same chart provided by the manufacturer on the same equipment. You do not use the chart provided on a different equipment. So, here we have a rebound hammer, as you can see the rebound number can be read from this very scale, and there is a chart provided over here which gives you estimate of the compressive strength of concrete. This is your ultrasonic pulse velocity meter, which we have already discussed. Then we have half cell potential, which gives a measure of the corrosion activity of the reinforcing steel. Here I have shown a sample test being conducted to assess what is the corrosion activity of these steel, and this is contained in IS 516 part 5 section 2 2021. Then you can have more tests which are related to durability of concrete, such as carbonation and pH tests. This gives you a measure of ingress depth of carbon dioxide and a potential loss of the passive alkaline layer around the steel rivers. Let us say that the carbonation depth is 10 millimeters. Then we can say that the reinforced concrete is still safe because the carbonation has not reached the steel, because carbonation leads to loss of passive alkaline layer around the steel rivers that can lead to corrosion. Now, if your carbonation depth is, let us say, 60 millimeters, then in that case that passive alkaline layer would have got broken and the steel rivers would be facing corrosion. So, the carbonation depth is obtained using this very IS code IS 516 part 5 section 2 2021. You can also conduct RCPT test or rapid chloride penetration test, which is giving a measure of chloride attack on concrete leading to deterioration. More details are available in IS 14959 part 2 2001. You can also conduct other durability tests such as density, water absorption, water permeability, and so on. Now, if your non-destructive testing provides you a result which is believable, what I am meaning by believable is that if you conduct UPV and rebound hammer at the same location and both of them give you good values, then you can rely on that value. But if both are giving conflicting values or both of them are giving inferior values for concrete, then in order to be sure about the quality of concrete, we shall perform some laboratory tests. I just gave an example related to these two equipments which are most commonly used. However, this is true for all non-destructive testing. So, we can have a core compressive strength test. This is a figure where we have been extracting concrete core, and after extracting the concrete core, we can test it in a laboratory to obtain the compressive strength of concrete. This is a very deterministic test. This is not an estimate. We directly do the test on the extracted core, and therefore it is more reliable than the non-destructive testing such as UPV and rebound hammer. So, these are usually conducted if the NDT results are not conclusive, and this is based on IS 516 part 1 section 1 2021. There are other tests such as microstructural tests. We can collect powder samples and do XRF or ACM to understand phase change in concrete. So, these are the microstructural tests which we can conduct in our laboratory. After doing the condition assessment of the building components and building material, we shall go to capacity demand evaluation. In the capacity demand evaluation, we will evaluate capacity and demand. In capacity evaluation, we evaluate or determine probable component strength of primary lateral load resisting system, particularly at critical sections. So, we find out the probable flexural strength at critical sections of beams and columns, probable shear strength at critical sections of beams and columns, then probable flexural and shear strength of joints, and then we use knowledge factor depending on how much information do we have about the building. We will use a knowledge factor and then reduce the strength to acceptable probable flexural strength or shear strength, whatever be the case. So, that shall be our capacity of the components of the building. Then we will move to demand evaluation, where we will find out the modified lateral force and resulting member actions. In this case, we will use different methods such as linear equivalent static method or dynamic analysis method to obtain the design base shear, and then we will reduce that design base shear by usable life factor, which is usually taken as 0.7, and then based on this we shall perform a structure analysis to obtain resulting member actions. So, in this case we will include all the concrete and masonry components in the numerical model, which means that we need to consider the infill walls as well, and then the component stiffness may be obtained rationally. This is based on table 2 of IS 15988-2013. As you can see over here that the stiffness of various components is provided. I have adopted that table 2 over here as well for your convenience, but I hope you have the copy of the IS 15988 ready with you. Now, once we have the demand or capacity known to us for various components, we can also calculate the demand capacity ratio, and if the demand capacity ratio is within 1, we can tell that the components are safe, and if it is exceeding 1, we can say that the components are not safe and therefore they will need some retrofit strategy. We will also check the interstory drift against acceptable limits specified in IS 1893. Now, after doing the capacity demand evaluation, we will also do some more checks which are called as acceptability criteria. The first thing is that we need to satisfy either of the following two criteria, which means it may happen that all the critical elements of the lateral force resisting system have probable strength or the capacity greater than the resulting action or demand, which means demand to capacity ratio is less than 1 for all critical elements. The drift checks are also satisfied as per limits specified in IS 1893 part 1 2016, or if all of the critical elements are not satisfying this, but most of them are satisfying, and the failure of critical element not satisfying this are not triggering any loss of stability or they are not initiating progressive collapse, and the drift checks are satisfied, then in that case also we can accept the building, that is we can say that the building has satisfied the acceptability criteria. So, either all the critical elements are satisfying the demand to capacity ratio being less than 1, or most of them are satisfying, and those who are not satisfying are not triggering loss of stability or progressive collapse. The drift check need to be satisfied in either case. Any of these criteria is satisfied, well and good, the building is satisfying the acceptability criteria. Now, apart from the acceptability criteria, we will look into some more criteria which are related to ductility and detailing. So, in ductility and detailing related evaluation, let us look into the moment resisting RC frame building. In the ductility and detailing related evaluation, let me state that if you find some deficiency, then you shall be using the lower value of response reaction factor. The code does not give information about how much value of response reaction factor, what shall be the lower value, but I hope for that you can refer to specialist literature. Then in this case, we need to satisfy a few conditions. If these are not satisfied, we will call it deficient in ductility and detailing, and then we shall use lower value of response reaction factor. What are the different conditions? Let us look one by one. No shear failure. The building should have adequate shear capacity to develop moment capacity at ends of its members in accordance with IS 13920. The column foundation joint should have adequate anchorage of columns into foundation from top of pedestal. Then the strong column weak beam philosophy has been followed. It tells that the sum of moment of resistance of column must be at least 1.1 times the sum of moment of resistance of the beams at each frame joint. Our code IS 13920 gives a higher value of 1.4, which itself means that if you have detailed it as per IS 13920, then it will always be satisfied. But if you have not used that, or if you have a building which is designed and constructed before that code came into picture, then in that case you need to check this strong column weak beam philosophy whether it is satisfied or not. Then we will also check the ductile detailing requirements in beams and columns. Related to beams, we will have ductile detailing for longitudinal reinforcement and transverse reinforcement. For longitudinal reinforcement in a given beam, we will have at least 2 bars at top and 2 bars at bottom throughout the beam length. You cannot curtail the bars near the supports even at bottom, even if you do not have any sagging moment over there. Then at least 25% of the longitudinal bars have to be continuous throughout the beam length. Then related to transverse reinforcement, the stirrups should be anchored into member cores by 135 degree. We have seen this in more detail in week 5 and 6 of the course. This gives very good confinement to the core concrete. The spacing of link also has similar specifications which are also given in IS 13920. So this gives about the maximum spacing that you can provide for stirrups and the maximum distance of the first link from the column face, which should be 50 millimeters. If all of these things are satisfied, we say that the ductile detailing in beam is followed. If these are not satisfied, then we will say that the building is deficient when it comes to ductile detailing of beams. We also have some provisions related to splicing in beams, which is prohibited within a joint and within 2D from the joint face and within the quarter length of member near supports. The splice length also has to be at least equal to the development length in tension. The hoops should be at maximum spacing of 150 millimeters center to center. Then we will not be splicing more than 50% bars at the same location. If we happen to do that, then we shall increase the splice length by 30%. If all of these are satisfied, then we can say that the beams are properly detailed for ductility. If these are not satisfied, then we will say that the building has deficiency when it comes to ductility of beams. Now let us look into ductile detailing in columns, again related to stirrups, which need to have a hoop of 135 degree and the maximum spacing of parallel legs of the links should be 300 mm center to center. All these details we have seen in week 5 and 6, where we were looking about the ductile detailing based on IS 13920. The splicing in columns should also be followed, that is, the location should be the central half of the column height. The splice length should be equal to the development length in tension. The hoops should be at maximum spacing of 150 mm center to center, and we should not be splicing more than 50% bars at the same location. If you have to do that, then the splice length shall be increased by 30%. Then related to beam column joints, the maximum tie spacing can be 150 millimeters. Now if these conditions are satisfied, we say that the building is safe when it comes from the perspective of ductile detailing in columns and beam column joints. If any of these conditions is not met, we say that the building has deficiency in relation to the ductile detailing of columns and beam column joints. And if the building is found to be deficient from these ductile detailing perspective, then we shall use a reduced value of response reaction factor. So we shall have an increased value of demand and then we can again evaluate whether the building is safe or not when it comes to demand and capacity. Now, let us look into some ductile detailing provisions related to infill walls, which says about allowable height to thickness ratio of unreinforced masonry infill walls, which are obtained from table 3 of IS 15988 depending on seismic zone and the wall type. As you can see over here, there are some guidelines about the allowable height to thickness ratio of parapet walls as well, which is given over here and obtained from table 4 of IS 15988. Now, let us look into shear wall buildings. Again, the premise is the same. If your shear wall building is found to be deficient when it comes to ductile detailing or the ductility and detailing related evaluation, then in that case we need to use a lower value of response reaction factor to estimate the demand on the building, and as such, because of the lower value of response reaction factor, the demand will increase, and then we can conclude again whether the building is having an admissible demand to capacity ratio or not. So, in this case we will check some of the conditions, such as the minimum thickness of the walls shall be based on ordinary shear wall or a special shear wall or coupled shear wall shall be 100 mm or 150 mm or 200 mm. The aspect ratio of the wall shall be between 1 and 4 to resist overturning moment, and this is true only for shear wall and not for wall piers. The longitudinal reinforcement shall be expressed in terms of gross area of the shear wall depending on whether it is an ordinary shear wall or a special shear wall. Then we have also clauses related to transverse reinforcement, which is again expressed in terms of the gross area of the shear wall. We have specifications for coupling beams, where the maximum strap spacing shall be d by 2 and these straps have to be anchored into member cores by 135° hooks. Then the opening in wall shall have a maximum total length of 75% of the length of perimeter wall, and there should be adequate shear transfer connection between slabs and the walls on which they are resting. So, if these conditions are satisfied, then the building is good to go. You do not have to reduce the value of response reaction factor, but if any of these conditions are not satisfied, then you have to reduce the response reaction factor. The reduced response reaction factor will lead to increase in seismic demand, and therefore the demand to capacity ratio may come close to 1 or may even exceed 1, which will suggest you to provide suitable retrofitting strategy. Now, our code IS 15988 does not give information about how much response reaction factor to be lowered. Maybe in the further versions of the code that should be added, but that can be obtained using a specialist literature. So, summarizing, in today's class we have discussed about detailed evaluation related to reinforced concrete building, and once we understand that, and once when we conclude depending on preliminary and detailed evaluation that the building needs retrofit, then we have to choose suitable retrofit measure. In the next class we will look about seismic retrofit strategies and how do we implement them. Thank you.